Hello ladies and gentlemen, welcome back to my channel. Okay, let's continue with our aircraft design tutorial. Okay, continuing from the last video that we had our aircraft design. So today we'll be continuing the project, okay, by adding the flow domain, okay, to the aircraft, and then we'll continue with the meshing and setting up the simulation. So now, okay, we have got our aircraft in 3D. So now we have to go to this XY plane, okay, and we will add our new sketch here, okay, and let's go into the sketching mode and draw the flow domain like so. So imagine the flow domain is like the rectangle, okay, it's like the wind tunnel, okay, so we are putting our aircraft inside the wind tunnel. So now we have to size the domain properly. Okay, so the horizontal distance from this part to this part is 5 to 10 times, okay, the characteristic length. So the characteristic length we are using here is the chord length of the aircraft, okay. So in this case, what is the chord length of the aircraft, of the aircraft wing? Okay, I'll need to, okay, let's do this. Okay, it's like 7 meter. So 5 times 7, H20 will be 35 meters. 35 meters like so, okay, and then the distance from here to here is 10, okay, to 15 times, so that will be like 7, it will be 70, right? 70 plus 7, so it will be 77. Okay, more or less 77, okay, or let's make it 80. And then the horizontal distance from here to here, okay, and from here to here, that will be 35 and 35. Right, so that will be the size of our flow domain. Okay, let's go back to the modeling mode and let's extrude the sketch. Okay, we want to extrude it by using this one, add frozen, okay, and then extrude 35 meters to the side like so, okay, 35, right, then hit generate. Okay, so remember, because the flow is going to be symmetrical on the XY plane, so we will be only simulating this side, okay, of the domain. So the other side, okay, the flow field will be symmetrical to this one, so we only need to simulate this part. Okay, now we have to carve the aircraft, okay, into, we have to carve the aircraft into the flow domain. Okay, so we have to subtract, okay, using the boolean, and then subtract the target body is the thing that we want to carve into, and then this is what we want to cut away, right? And then preserve to body, click no, then hit generate. Okay, now we have our what is that, aircraft carved into the domain like so. Okay, and then the next thing we want to do, okay, the next thing we want to do is to name all the surfaces involved. Okay, We want to name all the surfaces. Okay, next I want to hide sketch. Okay, yep, and then select this one. Okay, so we'll start by naming this face. Okay, I'll call it symmetrical face. Okay, I'll call it symmetry, like so. Then hit generate. Once I've named the face, okay, I'll just have to hide it, okay, so that later on I'll know, okay, which faces I have not named yet. And then this face, the top face and the bottom face here, I'll call them far field. Hit generate, select, right click, hide faces. I forgot. Okay, I like to name this one far field as well, so I'll just go back to far field, select this face, right click, no, I have to delete, show hidden faces, delete, yes, okay, bottom face and side face, okay, total 4 faces, name selection, far field, then hide them. Okay, and then this one I'll name it outlet, generate, okay, hide it, okay, let's zoom in. Okay, let's start with this nose tip, right? Okay, so this face, okay, name selection, hit apply, I'll call it nose hyphen tip, generate, then hide the face, okay, and this part of the nose, okay, I'll call it nose body, generate, nose body, right click here and hide. Okay, and then the fuselage, okay, I'll call this entire thing fuselage. Hold on, this part, that part also. Okay, I'll just click this one and this one. Okay, let me just flip around. Okay, yes, that two big parts. Okay, I'll just call them, okay, fuselage, generate, and I'll hide fuselage like so, hide face. Okay, and this part over here, I'll call them, okay, this part over here, I'll just call it canopy, right? Okay, I'll use box select for this one. Yes, right click, name selection, apply, canopy, generate, then hide face. Okay, and then okay, Now I need to change this back to single select. Okay, I'll select this part. Okay, so this part I'll call it wing leading edge, right? So select, name selection, apply, call wing LE. Okay, sorry, this one LE. Okay, LE stands for leading edge, and then I will hide it. Okay, and this part and the bottom part there. Okay, and okay, this part I'll call them right click, name selection, apply. This is wing panels, generate, hide them, right click, hide them here. Okay, now the trailing edge. Okay, so let me just zoom in. Okay, so this part over here. Okay, this part, that is wing trailing edge, right? So right click, name selection, apply. This is wing TE, trailing edge. Okay, hide it, and then the other side over here. Okay, this is our fin trailing edge, fin TE. Hide face. Alright, then we have the, okay, let's use this one. Okay, let's zoom in. Okay, okay, right click, name selection, apply. So this one I'll call it edge tip. Okay, wing tip. I would name the edge for the wing tip. Okay, and then the face. Okay, create name selection, apply, and call it wing tip. Right, so we have a name selection for the edge and name selection for the face. Okay, because later on in fluent meshing, okay, we want to size the edge separately. So this one, hide face. Okay, and this part as well, I want to name this edge, the curved edge only. Hold on, okay, it should be like so. Zoom in. Yes, I want to name the curved edge only. Right click, name selection, apply. This is edge tip fin. or just call it edge fin. And then select face, right click, name selection. This is called fin tip. Okay. Yes. And then hide it. Hide face. Then the next thing is I'll use box select and select everything here. No way. Okay. Wait. Okay, change it back to single select. Okay. Okay, this part I'll name it differently. Okay, this one I'll name it exhaust. That face I'll name it exhaust. Okay, and then I'll hide the face. Okay, this part and this part, right click, name selection, I'll call it nozzle. Alright, and then I like to name this and this and these three edges. Right click, name selection, apply, edge, nozzle, generate. Right, and then right click, hide faces. Okay, now we want to check we don't have any faces, okay, that we have not named. Let's unhide the nozzle. Okay, show hidden faces, and I'll need to unhide I need to unhide the trailing edges as well. So this one, show hidden faces, show hidden faces. Right. Okay, so we will need to edge nozzle. Okay, so we need to redo this one. Okay, I only want this edge, okay, for the nozzle. Okay, so I'll select this one. First, we need to delete that edge nozzle. Okay, right click, name selection, apply. This is edge nozzle. Okay, and then for the trailing edge, we will need to name the edges as well. So that is the trailing edge for wing, edge, okay, TE wing, generate, and okay, these two edges are for the fin. Right click, name selection, edge, TE fin, generate. Sorry, so this one, okay, so this one should be edge for the exhaust, not nozzle. Okay, let's rename it exhaust. Yes, and edge nozzle is that too. Right click, edge nozzle, generate. Okay, now we are done with the geometry. Okay, now let's move on to fluent. With fluent meshing, right? And then activate the mesh, double precision. So I'll use 30 processors. Okay, so the next thing we need to do is to import the geometry. Okay, would you like to add local sizing? Yes. So we will start with the nose tip. Okay, the nose tip minimum size is 1 mm. Okay, we use curvature for this one. Minimum size is 1 mm. Maximum size is 2 mm. And curvature normal angle I'll use 12, right? Scope to faces. And for nose body, the next one, minimum is 5 mm. Okay, to 0.1 meter. This one is 15 as well. No, this one is 15. Add local sizing. And then the fuselage and canopy. Right, minimum is 0.1, maximum 0.2, 15. This one include the nozzle as well. Okay, add local sizing. Then exhaust 0.01 minimum, maximum is 0.1. This one is 12. Exhaust. Next is wing leading edge, wing LE. Maximum is 5 mm, minimum is 1 mm. This is 12. The curvature normal angle, scope to faces, yes. And then wing panel, wing and fin panels, wing panel, and if you have fin panels, okay, the sizing should be the same. Minimum 0.01, 0.05. This one is 15. Add local sizing. And then tip. Okay, for the wing tip and fin tip, the edge sizing minimum is 0.001, 0.002, that's 2 mm. Curvature normal angle is 10. Scope to edge labels, we want to add it to the wing tip and fin tip. Yes, right. And then we want to size the curvature, the edge of the exhaust minimum is 5 mm, maximum is 10 mm. This is 10 for the exhaust edge labels, yes. And then we'll use proximity for trailing the wing and fin trailing edges. Proximity for the wing is 0.002, that's 0.2 mm to 2 mm. We want to have 2 cells across them, across the 2 edges, so TE, wing, yes. And we want to add the proximity 5, 0.00 to 2 mm. We only want 1 cell across the edges, edge, trailing edge, fin, yes. Okay, next we are ready to generate the surface mesh. Okay, minimum is 0.002. Okay, maximum is 6. Okay, let's keep the default. Let's keep it to 3. Okay, generate. Okay, so the next thing is to describe the geometry. So the geometry consists of only fluid regions with no voids, and then we don't want to apply shear topology. Okay, describe geometry, and then update boundaries. Okay, just want to check. Okay, the far field, the boundary term is pressure far field. Okay, and then the outlet, the pressure, the boundary type is pressure outlet, symmetry. Okay, and then everything else is wall. Update boundaries, update region. Okay, make sure the region type is fluid, and then add boundary layer. Okay, we'll use last ratio for this exercise, and then we want to have 5 layers. Okay, first cell height is 0.2 mm. And we'll use polyhex core. Pure layers, we'll put 3, and generate poly mesh. Okay, so we've got mesh ready. So the minimum quality is 0.14, which is larger than 0.1. That's very good. Okay, next is to switch to solution. Click yes. Okay, so we will use the Spalart-Almaraz model, one equation model for turbulence modeling. Then click OK. Next thing is you have to make sure the fluid is air. By default, it should be air, right? And then since we are going to model compressible flow, okay, for this case, because the aircraft is traveling at Mach 0.6. Right, so so energy equation, you have to turn it on, click OK. Okay, and then you have to go to the materials, air. Okay, density, you have to change it to ideal gas. Okay, change to ideal gas. Then create, change, close. Okay, then the next thing is the inlet. Okay, double click on far field. Right, so Mach 0.6. Okay, click apply, close, and the reference values, okay, you want to compute from far field. Where is the far field? Here. Okay, this area, okay, is the where's that, wing area. Okay, the wing platform area. Okay, since we are modeling only half of the aircraft, so only one side of the wing platform area will be used here. Okay, so for now I'm just going to put one here, and method, okay, we use simple. Okay, and then turbulent viscosity, okay, second order upwind, and then click on this one, high order term relaxation, to help with the convergence. Then report definition, we want to monitor the lift and drag of the aircraft, so I'll put CD for drag coefficient. Okay, select everything here and print to console. I don't want to create report file, but I want the report plot and print to console. Hit OK. New surface report, I want to monitor the lift coefficient as well, CL. Okay, select everything here, uncheck this one, check print to console, hit OK. Close. And then here the residual. Okay, I want to make sure that the CL and CD, okay, will reach, this is the difference, okay, the delta CL, okay, the change of CL is less than 0.001, okay, every 20 iterations, then only I consider the solutions converge. Okay, I'll do the same for CD, delta CD. Okay, so for every 20 iterations, I'll check the CD. Okay, I'll check the difference. So I want to make sure the difference will be lower than this value, then only I consider the solutions converge. Alright, then hit OK. So this one, okay, I'll put 10 to the power of -4. Okay, that's my convergence criteria. Right, hit OK. Okay, I'll use hybrid initialization, initialize. Okay, now the initialization is done. Okay, we'll continue with the run calculation. So I will expect to get convergence within 2000 iterations. Okay, and then the data file quantities here, you may want to check the pressure coefficient as well. Okay, and then maybe you want to see the Mach number if you want to plot the Mach number contour in the results later. Okay, I think that's for all. That's all for now. I think that's all for now. Okay, then calculate. And let's wait for the results. Okay, the solution is now converged. Okay, let's check the results. So this is the residual plot, so everything is converged, that's good. And then we can see that this drag coefficient has reached steady state. So the final drag coefficient is about, where is the C? 0.283, something like that, CD. Okay, then let's have a look at CL, the leap coefficient. So this is 2.8 something. Okay, remember this is calculated based on your reference values. Okay, what is that? The area, the reference area that I use is 1 meter square. Okay, so in reality, okay, you have to calculate using the planform area. Okay. So if you go to report, okay, let's and then you go to forces. Okay, I want to get the drag, okay, for the entire aircraft. Click print. Okay, so you get to see, okay, so the forces, okay, contributed by each components here. And then you can see the pressure drag, for example, from the canopy, the viscous drag from the canopy, okay, and so on. And then you can check the coefficients as well, right? And then this is the total drag coefficient that you're gonna get, okay, from all these components, and the total drag force from all these components. Okay, you can do the same for lift as well. So all you need to do is change to x0 and y from 0 to 1, then print. Okay, so same thing, canopy, so the pressure force is 2,954 newtons. Okay, and this is the viscous force, okay, contributed by canopy. Okay, and this is the net. All right, so the next thing we want to check is the results, the contours, for example. Okay, double click on results here. Okay, so you want to check the pressure contour, let's say. Okay, pressure contour. Okay, I want the pressure contour to be on the symmetry plane. Okay, this one I'll put 50, and then Alright, so this is the pressure contour. Okay, so if you want to check the velocity contour, okay, you just have to rename this one to velocity, right? Then hit OK. Then location, you want it on the symmetric plane as well. So this one, put 50. Okay, variable here, change from pressure to velocity. Then hit apply. Okay, then I'll turn off this pressure contour. Okay, so this is the velocity contour. And if you want to plot the velocity vector, you can click on this one. Then hit OK. Okay, location on the symmetric plane as well. Reduction factor we'll keep 1. Symmetry sampling, right? So hit apply, and I want to turn off the velocity contour. Okay, so this is the velocity vector. It looks awful. Okay, let's go and change the symbol size. Okay, I want it smaller, 40% small, 60% smaller, right? So I'll just hit apply. Maybe I can further reduce it to 0.1. Yeah, it looks better. Okay. And what else? Okay, maybe we want to check the Mach contour. Okay, Mach number, hit OK. Mach number, where is the Mach number? Okay. Alright, so in order to get Mach number, okay, first you have to go back to this one, Fluent, and change the preference. You want to save the result in legacy format, hit OK. Alright, and you have to run the calculation for one more iteration. Then you check the quantity. Okay, now you should get pressure coefficient, Mach number. Okay, you have to have these two selected if you want to get the pressure coefficient, okay, in the results, and Mach number in the results. Then hit OK. Then hit calculate. Okay, so let's go back to this one, refresh. Okay, the new results are loaded. So let's go and check for the Mach number. Okay, I want it on symmetry. Okay, mark number. Okay, this one I'll put 50. Hit apply. Okay, let me just turn off the vector. Okay, now we've got the map contour. Okay, maybe I'll just change it to local. Right. Okay. Okay, so this is it for this tutorial. Okay, thank you very much for watching.